So in this video, I'm going to be exploring the peft DoRA implementation. And I've gone through this code a couple of times, so it should be pretty smooth, hopefully. But I'm still wrapping my head around how DoRA is implemented, so it might be a little rough. I'm also working on a research paper summary video for DoRA, and so I'm going to start with the main concepts that I'm covering in this video, which is really this diagram from the paper. So we start with a D by K pre-trained weight matrix, W naught, and that's decomposed into a trainable vector, M, and M is 1 by K, so the elements of M are norms of each of the initial pre-trained weight matrix columns. And we also have a direction matrix, which is basically the original matrix divided by the norm. So each column in the direction matrix is a unit vector, and the magnitude of which is in the magnitude vector. And then we split the directional matrix into LoRa adapters delta V. And so we're only training a subset of the pre-trained weights. And then so we get this 1 over norm of the pre-trained weight plus the LoRa weights multiplied together, multiplied by the direction unit vector, kind of unit vector column matrix, and that gets multiplied by the final magnitude. And note that this decomposition is the initialization, so the initial magnitude is of the initial weights that have not been trained, and then the final magnitude is a completely different vector, right? So these are trained parameters, so we're doing gradient updates on them and everything during the training loop. So this final magnitude vector is completely different than the initial magnitude vector because it's a trainable. And so the benefit of this is that we train a lot less parameters because we're only training the LoRa adapters and we're only training the magnitude vector. And then the benefit of splitting this into magnitude and direction is that it shows that it learns patterns closer to full fine-tuning than LoRa is to full fine-tuning. So as you can see, in progress of making my DoRA slides, but I wanted to at least start with this concept. So in my code, I have a bunch of these imports. All of these are from this DoRA.py script that we're going to look at. I'm going to use the small LM2 135 million parameter model simply because that's something I've been using recently in tutorials. And I make my auto model for sequence classification. And then I have my LoRa config, which has a rank of 256. It's not using RS LoRa. It is using DoRA. And then I'm targeting these modules. I then get my peft model, and then I can see that, okay, only a third of the parameters are trainable because most of them are frozen. So the first thing I'm going to do is look at the model itself. And so it's a peft model, then it has a base model, which is the LoRa model. Then inside that we have the llama for sequence classification model. Inside that we have a llama model, and then we have the actual layers. So I'm going to go into the base model, into the model, and the second model. So this should bring me to the llama model. And now I can access the layers. So I'm going to do that. And I have 30 layers, and they're decoder layers. So I'm just going to grab the first one. And now I can see that I have my self-attention, which has Q, K, V, and the output. And then I have my MLP layer, which has a gate layer, an up projection, and a down projection. And there's also a couple layer norms. So for this exercise, I'm really curious about the shapes of the magnitude vector and the directional matrix. So I don't want to pick something that is a square matrix. So I'm not going to pick Q, but I'm going to pick the K projection layer because that is a rectangular matrix. So the shape will tell us about, what's being considered for what purpose. So I'm going to get the self-attention block, and then I'm going to get kproj. Okay, so this is a LoRa linear layer, and that's the main outer layer. And inside the LoRa linear layer, we have a base layer, which is our pre-trained weight matrix. And then we have a bunch of LoRa related things. So main interest for this video is LoRa A and B. LoRa A goes from 576 down to 256. LoRa B goes from 256 to 192. Now, I've chosen a large rank, and so I actually end up having more parameters with LoRa because 192 is smaller than my rank of 256. I'm not going to worry about the embedding layers in this video, but I am very much going to worry about the LoRa magnitude vector, and that is of type DoRA linear layer. Okay, so I think this is a good point where we can step into the DoRA codebase. So in the peft library, under source, peft, tuners, LoRa, and there's a DoRA.py, which is of main interest. And inside DoRA.py, we have this DoRA linear layer, which is this guy right here. And then if we look at LoRa, the LoRa tuner folder, and we look at layer.py, we have this class which is called linear, which is all the way up here, linear, and it inherits from the LoRa layer. And if we scroll down here, I'm particularly interested in the forward pass because that's going to tell us how it's utilizing DoRA. And here we can see the repra is LoRa.linear. And so that, my understanding is that's this layer here. So kproj is this LoRa linear layer, and then our LoRa magnitude vector is the DoRA linear layer. All right, so that's some preliminary items. So I think I can now get into this, and I'm going to say, let's look at our kproj base layer, which should be this regular linear layer. And if we look at the shape of weights, we can see that the order of weights is the output neuron size, or number of output neurons, and the number of input neurons. So in features is 576, that's the dimension of 1. Out features is 192, that's the dimension of 0. So key point is the order of the in and out features. So here it's out, comma, in. So it's something we'll return to in a bit. And then DLL is going to be my DoRA linear layer, which is going to be the LoRa magnitude vector dot default. So if I go here, this is my DoRA linear layer. And a key point is this fan in, fan out. So I searched the code base for fan in, fan out, and I found a number of references where it says fan in, fan out is true if the layer has weights like in, comma, out. And so here's another one. Set this to true if the layer to replace stores weight like fan in, fan out. So in our case, it's not fan in, fan out because it's out, comma, in. So this should be false. So if we look at fan in, fan out, this should be false, which it is. All right, cool. So we know what our base weight looks like, and we know that the order of our input and output features is out, comma, in, and that's going to be important information as we look at things in the script. Okay, so I'll do a quick overview of how I was, understanding this code. So let me scroll up a bit, and let's see, I might have to search for DoRA init. Okay, so inside this layer, which, let's see, this is a very large class, LoRa layer. Okay, so inside this LoRa layer, there is a DoRA init method, and it does a lot of the initialization. So if we go back to this diagram, we're kind of in this initialize phase. So inside DoRA init, it defines the DoRA linear layer, and it sets this fan in, fan out variable, sets up LoRa adapters, I'm not going to go into detail there, but the key thing here is that it does this thing here. So it does DoRA layer dot update layer, and it passes the base layer, the LoRa adapters, the scaling factor, and then it assigns this DoRA layer to the LoRa magnitude vector. So if we go to the DoRA.py and we look at update layer, the of most interest is how it calculates the LoRa weight, which is LoRa B matrix multiplied by LoRa A. And then it calculates this weight norm, which is the magnitude of the weight plus the LoRa weight. So we'll look at get weight norm in a second. And it then makes weight norm a trainable parameter. So NN parameter. So this is what we're looking at here. In green, this magnitude is trainable, and so that's what's going on here. And then it assigns it to self.weight, which is important because we're going to see that again in the forward pass of the DoRA linear layer. So what does get weight norm do? So we're going to skip to that. This is again still inside the DoRA linear layer. Get weight norm, first it checks if this weight needs to be transposed, because we want to get column-wise, we want to make sure that, basically we want to make sure that the number of values in our weight norm corresponds to the number of output neurons. So we want to make sure that we have one element per output dimension, number of output features. So let's do that here. So I'm going to say weight equals transpose, and then I'm going to grab this weight and then I'm going to grab my fan in, fan out value, and I'm going to look at the weight shape. So it did not change. So transpose did not change the weight shape. So if we look at their utils other.py and we look at transpose, if not fan in, fan out, don't transpose the weight. Just return the weight as is. So fan in, fan out is false. Not false is true. So if true, return the weight. So, okay, our weight is in the appropriate shape, and in the appropriate shape is out dimension first and in dimension next. Okay. So that's this line. So we got our weight. Next, we need to do weight plus scaling times LoRa weight. So I'm going to say my scaling, I'm just going to put that as 1. And then my LoRa weight, if we go back up here, is kproj.LoRaB.default.weight matrix multiplied by kproj.LoRaA.default.weight. So LoRa weight equals kproj.LoRaB.default.weight matrix multiplied by the same thing but for LoRa A. And if we look at the shape, it should be the same as our pre-trained weights, which it is. So out features, comma, in features. So I set my scaling, I have my LoRa weight. Now I'm just going to grab this and check the shape, which should be 192 by 576. All right, great. And then the key thing, the very important thing that we're doing here is we're going to take the norm of our weight, and our weight is our merged, pre-trained, and LoRa weights, and these are, we're at the initialization stage of this. And we're going to take the weight, the norm of the weight across dim equals 1. So we should end up with 1 norm value per output neurons. And to match the forward pass later on, I'm going to call this magnitude. And also this kind of matches this M over here. So if we run this and we look at the magnitude, we have 192. So for each output neuron, or each column, however you want to look at it, we have the magnitude of that column. So that's what we get here with weight norm. And that's what our update layer does. So if we go to update layer, it did get weight norm, so we got our weight norm. And then we have stored that as self.weight. So this is now a parameter. And just for completeness, I'm going to do this. And hopefully that will not break anything later on because I didn't do this the first time. So this should be 192. Okay. All right, cool. So we have done our kind of DoRA init stage. So the next thing I want to look at now is what happens during these different forward passes. And I'm going to start with the DoRA linear layer forward pass in terms of going in detail, but before I go into detail, I do want to look at our linear layer, which is not in here, but is in layer.py. So let's look at linear. I think it's, yeah, this one. Okay. So as a reminder, our kproj is a LoRa.linear layer, which is this one right here. So if we look at the forward pass for this one, I'm going to skip some of these details. I think I can skip these. So we're not worrying about disable adapters. We're not setting adapter name. We're not doing merged. So we're doing this else. So this else block is of interest. So first it grabs the result, which is passing our input X through the base layer, which is our pre-trained weights. It gets our LoRa's, it gets our scaling. If not self-use DoRA, so this is use DoRA is true, so not true is false, so we don't do that. So we go into this else block, does some dropout, but this is the key thing here, because this is what it's going to result, is what it's returning from the forward method. So this result is our initial result, if we go back up here, which is the pre-trained weight base layer. So it's the result plus whatever the output is of our LoRa magnitude vector, which was our DoRA linear layer forward pass. So just keep in mind that we're adding our base layer output to whatever the output is of our DoRA linear layer. So keep that in mind as we look at our DoRA linear layer. So just to double check, here's DoRA linear layer, and this is DoRA linear layer. So this is what we're really focused on right now. So okay, let's look at what's inside there. So we get magnitude as self.weight. So I've already got that ready. And then the first thing we're going to do is we're going to get the base layer weights. So I'm going to drop that in there. And our base layer is kproj.baselayer. So this should be our same 192 by 576, which it is. Great. I don't think I need to run this because it's already done. And then here, I'm going to get the weight norm. So let's drop this in. And this is DLL. And we already have our LoRa weights, and that's good. So if we do our weight norm, this is 192. So key difference that I want to highlight is that magnitude, which was also using this norm, which was using the pre-trained weights plus LoRa weights, that was during the initialization stage. After that, it becomes a trainable parameter. So it diverges from whatever the actual weight norm was. What we're calculating right now in terms of this weight norm is this term right here, this 1 over the column, the vector-wise column norm of V plus delta V. So V is weight, delta V is LoRa weight. We add the two, and then we take the column-wise vector, so we get this 192. So during adaptation, so during training, this would be the actual norm of our pre-trained weights and LoRa weight matrices, or combined matrices. Whereas this magnitude is not the actual norm during training. It is during initialization, but as soon as we start training, this is now an NN parameter with required grad equals true. So this is whatever the gradients decide it is. So by the end, this magnitude is not really like a magnitude, it's like a learned magnitude. So that's one thing I want to distinguish. Something that they mentioned here, we suggest treating this weight norm as a constant, so we're detaching it from the gradient graph. And so it reflects the dynamic updates of delta V, so during training, but it won't receive any gradient during backpropagation. That's not super important. for what we're doing here, but I'll do it nevertheless. All right, in our forward pass of our DoRA linear layer, the next thing is we are doing magnitude divided by weight norm. So you see this multiplication sign is m times 1 over weight norm times the direction matrix. And so magnitude times 1 over weight norm is just magnitude divided by weight norm. And we're adding a unit axis to that. So if we look at mag norm scale shape, it should be 1 by 192. Cool. So at this point, I'm now getting a LoRa result. So I'm doing the matrix multiplication between my input X, my LoRa A, and my LoRa B. And in order to do that, I need to get an X value. So I'm going to do that here. It's just going to be some random numbers. Let's say I have a batch size of 32, a sequence length of 200, and embedding size of 576. Okay, so my LoRa result is a matrix multiplication between this up here. So I'm just going to grab my LoRa weight, and I'm going to transpose it so that it gives me the right dimensions to matrix multiply. And so now we see that we went from 576 down to 192. So that's what we do here. Bias is none. Base result is not none. We're subtracting this bias. I'm not going to go into details there, but just going back here, base result was, let's assume base result was none. We could go either way. So base result is none, so we're going to pass it through our weights, our pre-trained weights. So this is a linear layer which takes our input, the transpose of our weight matrix, where our weight matrix was the base layer. So this is our base result. And this should be 32 by 200 by 192. So we pass it in with 576. We get out of it 192. So this is as expected. Great. And then the final piece is our result DoRA. And I'm going to copy this, and then we're going to take a look at it here. It looks a little different from what we would expect. If we go back here, we are just taking our magnitude over our norm, which is called mag norm scale, and we multiply it by V plus delta V. So here's V and here's delta V. So what I would expect, and this took me a bit of conversation with Claude, what I would expect is something like this. Result times scaling. So mag norm scale plus times V plus delta V. And our delta V is scaled because that's what it's one of the hyperparameters in LoRa. But why is there this -1, right? So if we expand this, out, we get, I'm going to take this base result and I'm going to expand it into here and into here. So we end up getting this. We get mag norm scale times base result minus base result plus mag norm scale times LoRa result times scaling. And if I rearrange things a little bit, and I just grab this, we basically get what we expect from the paper, which is mag norm scale, m over weight norm, times v plus scaling times delta v, except we have this minus base result. And the reason we have this minus base result is because in our LoRa layer, our linear LoRa layer forward pass, we're adding the base result to the output of LoRa magnitude vector. So my understanding, which is coming from Claude, is that the reason they've done this is to make this modular, so we can just slap on this DoRA result to the same forward pass. So conceptually it's all the same, but because we're adding the base result here, we have to subtract it inside of our DoRA. So that's why we have this -1. Okay, so all that is good. We're going to do result DoRA.shape, and everything should work well. We get 32 by 200 by 192. Excellent. So this is my walkthrough of the peft implementation of DoRA. And this was something that was inspired by Sebastian. I think the key thing that I wanted to highlight was, honestly, it was this fan in, fan out parameter, because it really dictates how this weight matrix is handled, and how this weight matrix is handled in terms of its shape, whether it's 192 by 576 or it's transposed, is going to dictate the magnitude vector, because we're taking the norm across the first or the second dimension, so dim equals 1. And the magnitude vector, conceptually, is supposed to line up with the number of output neurons you have in your weight matrix, in your linear layer. So it's a big difference whether this is 192 or this is 576. Obviously, in terms of shape and having all of your calculations work out in terms of alignment of all the dimensions, but also conceptually, we are training the output neuron related magnitudes, because that's what's going to steer, how this model is going to handle the inputs. So I wanted to highlight that. As I mentioned, I'm working on a slideshow for DoRA as a research paper summary. So I'll be releasing that hopefully this week, if not early next week. Cool. So thanks for watching. The notebook here is down in the description, and I will see you next time.